In this video, I'm going to focus on freely falling objects. What is a freely falling object? Well, there's three things. Number one, it must be in the air. Number two, the object is not moving left or right horizontally. It stays in a vertical plane and moves only up or down. Third, the only force acting on the object is the force of gravity. It's also known as its weight. Note that in real life, air resistance is present. That would apply an additional force to objects in the air. But in algebra-based physics classes, we're staying away from air resistance. It's just too complicated. It requires calculus, and it's something that makes the problems a lot more complicated. So in this level of physics, pretend that air is not present and things move freely through the air with no resistance at all. Reference frames, it's what you'd expect. Anything moving upward, we're going to call the positive direction, and anything moving downward, we're going to call the negative direction. So there are several variables mixed into your equations that are vectors. They can be positive or negative, things like velocity and acceleration. So make sure you're focused on which direction the vector points when you consider positive or negative. Let's take a look at graphs of motion. We're looking at three graphs: position, velocity, and acceleration as functions of time. We want to sketch the shape of those graphs for the motion of a freely falling object, in this case the basketball over there on the left. And the basketball is only freely falling right after it leaves the person's hand and just before striking the ground. So restrict your analysis to that time frame. If you want to pause the video and try to sketch these three graphs on your own, go right ahead. I'll show you each of them in a minute. Let's start with the position graph. Naturally, I think we'd call the ground a height of 0 meters, so the ball starts well above that height and therefore has a y-intercept in our graph. Now remember, the slope of this graph, position versus time, is velocity. Since this ball is speeding up, I want to see the slope of my graph get steeper and steeper. So it starts almost horizontal and gets steeper and steeper as it picks up speed. So this is an object that is moving in the negative direction downward and is speeding up as time goes on. Let's look at our velocity versus time graph. This ball is released from rest, so it starts with a velocity of 0 right there at the origin. It's moving in the negative direction downward and is speeding up at a consistent rate. So this graph shows something that is starting at 0, is moving into the negative quadrant, and is getting faster and faster because it's leaving 0 meters per second. Sticking with velocity, let's focus on initial velocity. Now there's three things that a person can do to make an object a freely falling one. It's got to leave their hands, so they could just drop it or let it go, release it from rest. They could throw it straight up, or they could throw it downward. And each of those three things would have a different factor for what you're going to do with the initial velocity variable if you see it in a word problem. If the ball is dropped or released from rest, you're going to set your initial velocity equal to 0, since it's not doing anything at the beginning. If the ball is thrown upwards, you're going to make the initial velocity positive, and for whatever amount they give you. And if the ball is thrown downward, we're going to make that a negative starting velocity. So make sure you're focused on what's going on at the beginning of the problem as far as what you're going to do with the velocity variable. Back to our situation, now looking at the acceleration versus time graph. We're looking at an object that starts with no velocity and speeds up in the downward negative direction. So because the velocity is becoming increasingly more negative, we would define it as a negative acceleration. And that's why our data is in the negative quadrant. As far as why the data is horizontal, we look at the velocity versus time graph. It is a negative linear slope, a constant slope, and we've discussed that the slope of this graph is your acceleration. So because of the constant negative slope, we would get a constant negative value for acceleration. Kinematic equations, the same three as previously discussed, just mentioning that there are no new equations to teach for this topic. You're just going to want to apply these to your problem-solving scenarios. Freefall acceleration, often called the acceleration due to gravity. This is the known constant value for objects that are freely falling near the Earth's surface. That value is negative 9.8 meters per second squared and is often on your class formula sheet. Finally, just want to connect mass and freefall. Here we're looking at a smaller mass m next to a larger mass 2m. These objects will be released from the same height and at the same time. And the question is, which would reach the ground first? Well, many students feel that the heavier object will reach first, but in reality, you'd find that they would hit at the same time. Remember that in the absence of air resistance, which we're not considering, all objects will fall freely at the same rate, which is negative 9.8 meters per second squared. We can also look back at our kinematic equations and observe that the variable m, mass, does not appear. Another reason why mass is not a factor for objects that fall freely.